Within integration, I'm Karul Anwar Masai. Concept: the basic principle of process integration in resource recovery. In the context of process integration, a process stream could serve as a material source or material sinks. Consider the simple process shown in figure 9.1a. There are two process units which consume and generate the same resource at different concentration at the configuration shown in figure 9.1a. Both units consume fresh resource. Can we reduce the use of external fresh resource? Yes. If we can recover the resource from the orthodox process unit 1 and reuse it as the feedstock of the process unit 2. This process of reuse can result in a reduction of external fresh resource consumption. The inherent degree to which a particular resource can be reused can be determined using mass pinch analysis (MPA). The greater the amount of resource reused within a process network, the lower the external fresh resource required. Furthermore, a material source stream can also be fed into a regeneration unit to improve the quality of the stream before recycling it or feeding it into another unit, as shown in figure 9.1c and 9.1d. These approaches for resource recovery were first introduced by Wang and Smith in 1994 for wastewater reduction, the principle of which can also be extended to gas and utility systems. Mass integration. Mass exchange underpin the concept of resource recovery. A mass exchange operation is important to recover the resource and limit or eliminate the source of pollutant. A typical example in process industry is when mass exchange process units are used to transfer the targeted undesirable species from process stream known as rich stream to mass separating agent that act as a receiving stream known as lean stream, based on the separating equilibrium. Mass pinch analysis. There are 5 key steps of mass pinch analysis. The first one is plan audit on mass network. Analyze the plant network of the targeted resources through plant auditing. Second, data extraction. Identify the mass source and sink of the targeted resource with the potential to recycle and reuse. Third, target minimum resource. Determine the minimum fresh resource required for the analyzed network. Fourth one is design the minimum visible mass network. Design a mass exchange network to realize the minimum acceptable resource target. The last one, economic analysis and other assessment. When you assess the economic of the design network as well as the feasibility. This is the flow chart for mass pinch analysis. We have 5 steps here. And reaching the 5th step, economic analysis and assessment. The feasibility of the design, the acceptable payback period, design with safety and geographical constraint will be evaluated. If it's not feasible, It will evolve. You need to evolve and change the design mesh utility network. If it's feasible, then yeah, it's the final decision, final design. Step 1. Plan audit on mesh network. For mesh pinch analysis MPA, the boundary of the system need to be evaluated. For water pinch, the user need to establish the water and contaminant balance. For hydrogen, the user should establish the hydrogen balance. Water using processes can be classified into two main categories: mass transfer based and non-mass transfer based operation. So for mass transfer based, water is used solely as mass separating agent where fixed amount of contaminant is transferred from a stream with high concentration of contaminant to a stream with a lower contaminant concentration. MTB operations are known as fixed contaminant load problem. Example of MTB are washing, scrubbing, and extraction. For FC problem, the amount of water enter and leaving the unit are similar. Example of MTB operation. This is a vessel washing process. The water for vessel washing enter the vessel and the wastewater generated from vessel washing. Sour gas absorption. Water as the absorption solvent from the upper column and pass through the sour gas in which the gas turns sweetened while the water leaving the absorption column to the regeneration unit. Non-mass transfer based MTB. Function of water other than as mass separating agent. The water can be fed in a unit as a reactant or generated by process. The flow rate of water inlet and outlet may vary, and some cases inlet or outlet is non-existent. For example, to figure 9.7 here, two other common type of NMTB water using operation: cooling tower makeup and boiler blowdown. In this example, the flow rate of water inlet and outlet vary, and this is cases where the inlet or outlet is non-existent. This is the case where water can be fed as a reactant or generated by the process. Figure 9.6, an MTB water using operation. Figure 9.6a, water is consumed by a reactor in the production of aniline as a one of the reactant. 9.6b, water is produced as a byproduct in acrylonitrile production. The inlet and outlet water stream are characterized as sink and source stream that consume or generate fixed amount of water. This is similar to direct stream injection in heat exchange, which affect the overall heat and mass balance and act as a direct supply of both heat and water. Hydrogen distribution. For refinery hydrogen distribution, the three typical processes involve a hydrogen-consuming process, hydrotreater, hydrocracker, hydrogen-producing process, catalytic reformer, and hydrogen-purifying process, membrane separation, pressure swing absorption, and cryogenic separation. All of these processes are an MTB operation, and hydrogen fall under fixed flow rate problem. In general, the outlet stream of process unit are the source stream, while the inlet stream are the demand stream. Again, this is similar to heat exchange, where the output product stream tend to be heat source or hot stream, whereas input feed stream are usually sink or cold stream. Thank you.